Hi, my name is Tyler Balon from the Connecticut Institute of Technology at the University of New Haven. Today, I will speak about our research on Forensic Artifact Finder, also known as ForensicAF. It is an approach and tool for leveraging crowdsourced, curated forensic artifacts. Co-authors of the paper are Krikor Herlopian, Ibrahim Baggili, and Cinthya Grajeda-Mendez. Artifact analysis relies heavily on investigator expertise and resources. Today, we're going to present ForensicAF, an autopsy interest module which allows forensic examiners to use pre-existing artifact databases to aid in the discovery of artifacts which are forensically relevant to a case. On our agenda, we're going to briefly introduce our authors. We're going to speak about the motivation behind this project. We're going to see how the Artifact Genome Project made ForensicAF possible. Then we are going to compare forensic analysis techniques for a traditional method compared to using the automated process in our plugin. We're then going to look deep under the hood of ForensicAF, look at the design and the construction of the plugin, as well as how it is used. Finally, we will speak on how we evaluated the success of the plugin, the results of that evaluation, and what conclusions and future work we could derive thereafter. A little bit about our authors. My name is Tyler. I recently graduated from the University of New Haven with a master's in computer science. Krikor as well recently graduated from the university with his master's in computer science. We were both advised by Ibrahim Baggili, who is the director of the Connecticut Institute of Technology, an elder family endowed chair for the university. Cinthya is a university alum, graduating in 2019 with her master's. She's currently the UNH Cybersecurity Lab and Grant Manager, and she was one of the authors on the original work for AGP. Digital forensic investigations are time and resource intensive. Even experienced investigators can take days finding artifacts. This costs time in an investigation. ForensicAF uses the Artifact Genome Project, AGP, by leveraging the curated artifacts, CUFAs, inside the database to speed up the forensic examination process. Our work makes the following contributions. We conceptualize and implement ForensicAF, an open source autopsy plugin which aids in extraction of forensically relevant artifacts. We leverage vetted, crowdsourced repositories of CUFAs, like AGP, to extract artifacts which were deemed noteworthy by past researchers. We encourage forensic units to share artifacts among artifact databases and repositories. We evaluate ForensicAF's ability to locate relevant artifacts on a variety of digital media sources. During our evaluation, we use self-made media sources and publicly shared example case data from sources such as Digital Corpora to compare the analysis time, the artifacts which are found, and the relevance of those artifacts based on solution guides provided by the scenario creators. So how does ForensicAF find relevant artifacts? Artifact databases such as AGP store known artifacts. These artifacts are curated after they are submitted from various sources. These sources include academia and law enforcement and a variety of other sources. An example artifact which is found in AGP and information which is relevant to our usage is an artifact name, which will briefly identify the artifact, the type of the operating system which the artifact was found on, applicable device information. So in the example on the right-hand side, the Skype 8.10 username was found on an iPhone 6s Plus. In addition, there is a description of the artifact, which will briefly describe what the artifact is or how it is used. Hashes, so the artifact can be compared toward what is found on a data source. A download of the file, in case the investigator needs it. And the file name on the system where the artifact was found and the expected file path. The asterisks denote the fields used by ForensicAF to search and find these artifacts, which we consider might be forensically relevant. When comparing traditional methods to using the automation behind ForensicAF, traditional investigations can take hours of research across search engines, databases. It may even include research into how to reverse engineer applications. ForensicAF uses already curated artifacts from trusted sources such as academia, law enforcement, and submissions from the web. Say a law enforcement agency invests time into reversing a photo app and then submits that artifact to the Artifact Genome Project. Another forensic unit may be able to use that work by using ForensicAF, whereas if that information was not shared in some type of artifact database, they may have to do that reversing on their own. Now let's dive deeper into the design and the construction of ForensicAF, and we're going to see how successful our work actually was. When we look at the design and the construction, ForensicAF searches the disk via two methods. First, a file analysis performed by algorithm 1 seen on the right-hand side, and we're going to go into that in a second. And this algorithm will find CUFAs on the data source by traversing the file system. The algorithm will compare the file names found in the AGP entry and the file paths. If we look into algorithm 1, we can see that users can change the traversal level, which will determine how many directories back from the intended path ForensicAF will search on the disk and the subdirectories in that path to try to find the CUFA. From lines 2 to 6, this is just us creating variables for the paths, the names, the results, and of course the traversal level. From 7 to 9, this is the plugin actually iterating through the paths and names that we are searching for. From lines 10 to 13, we are then going through the different levels of traversal. In addition, ForensicAF will do registry analysis, and it uses a variety of Python libraries which simply query the Windows registry for existing keys which are archived in AGP. The libraries used to query the registry are listed on the bottom left-hand side of the presentation. So how do you use ForensicAF? Well, ForensicAF is written using Jython, a Java implementation of Python based on Python 2.7. It is built for Autopsy versions 4.16 and greater. The plugin can be retrieved from the UNHCFrag GitHub account. Example output provided by ForensicAF can be seen on the left-hand side. This is the registry tab, and this would be the example document which an investigator receives once running ForensicAF. You can see keys that were found on a data source that were also in the search query from AGP. If we were to go to the File tab, we would see, similarly, the file name, file path, and the option to download the file from the data source. Installing ForensicAF is as easy as 3 simple steps. First, using the Tools plugin menu from Autopsy, you would create a new folder called ForensicAF, and you would place the plugin in that folder. When Autopsy is relaunched, the plugin would then load. To download the CUFAs, you would need to register on agp.newhaven.edu. Accounts are manually approved by administrators, but once you are actually in AGP, you can either search for specific artifacts using the artifact search menu, or you could download all known artifacts in AGP and export these results. This is what ForensicAF will search for. When ForensicAF is ran, there are 4 settings which you can alter. You can either enable or disable the file artifact analysis, the registry artifact analysis, and if files should be exported, as well as set the traversal level for how many directories back ForensicAF should look for a CUFA. We did 2 types of evaluation. We did systematic and random sampling. During our systematic sampling, we built a data source with manually placed CUFAs, which were found in AGP. We scattered these files ranging from 0 to 4 traversal levels up from the intended path listed in the AGP entry. So on the left-hand graph here, we can see out of 100 possible CUFAs, at 3 traversal levels up, we found 98 out of the 100. This was intended as 2 were placed 4 traversal levels up, and the plugin should not have been able to see these 2. When we spread out the artifacts in different levels, we would go into subdirectories and place artifacts as well to make sure that the plugin was iterating through each directory properly. When looking at the time it takes for the plugin to run on this sample data, We can see in trial 1 and trial 2, the time was relatively the same, but as the traversal level increased, time grew. The time grows significantly as file sizes increase, and we're going to see that more in the random sampling when we start looking at disks of different data sizes. In this example, we had a clean installation of Windows, which we did this testing on. During our random sampling, we tested data sources which would have potential artifacts that could be forensically relevant to a scenario or a solution file. We used digital corpora forensic scenarios for this evaluation, as well as an image from the black t-shirt competition. On the left-hand side of the graph, we can see the comparison from level 0 traversal to level 2. On the level 0 side, meaning we were searching for the intended file path that was listed in AGP, we were able to find no files and, of course, all of the registry keys. But when we went up to level 2 traversal, we were able to find files on these devices, meaning that maybe they weren't in the intended place, which was listed in AGP, but they were still on the file system. It is worth noting that when you look up a artifact for the registry, we are simply querying the registry. That is why the traversal level does not impact if an artifact is found or not. There is a table on the bottom right, which includes the data sources, a brief identifier, the disk size, and the operating system of each data source. The right-hand graph looks at the sampling time. When we compare the times, it took ForensicAF additional time to analyze the data source when we go 2 traversal levels up, rather than going at the intended path. You can see that for the smaller disk images, this time doubled, and as the disk size grew larger, the time nearly tripled for the lone wolf scenario. So what did we actually accomplish? Using ForensicAF, we had the following accomplishments. When using a data source which we created, we were able to find all of the expected file and registry artifacts as we placed them on the system. The 2 that weren't found were intentionally not found, and it means that the plugin did not traverse higher than it was supposed to. When using random data sources, we were able to find artifacts which we can deem forensically relevant. The found artifacts can be seen in Table 5. Here in Table 5, we have 7 items total which were found. They were file and registry artifacts in the random data by digital corpora. We can see at M57, we had messaging app info and recently used apps. In the black t-shirt contest, we had computer usernames, recently used apps, and browser history. And in Lone Wolf, we also had recently used apps and browser history. We can deem these of forensic relevance because when reading the solution guide provided by Black T-shirt and Digital Corpora, we can see that these artifacts directly correlate to the solution. It would mean that if an investigator were to run this automated ForensicAF plugin from Autopsy on this data source before running manual investigation and having to actually analyze that file system themselves, they would be able to see artifacts appear from this automated process which may be of interest. For future work, we would like to extend ForensicAF to work with more artifact databases. And in addition, we'd like to provide some type of functionality for practitioners using ForensicAF to submit artifacts they may find to AGP or review to become CUFAs, as this will benefit everyone using ForensicAF, as the database will have more artifacts which they can search for on a file system. We're now going to be taking questions. We hope ForensicAF is able to positively impact digital forensic investigations by giving forensic practitioners an additional tool in their arsenal. It's not meant to be an end-all solution, but another automated step to help alleviate some of the time it takes to find important artifacts. We'd like to give a special thanks to the National Science Foundation, grant number 1900210, the authors cited in the references section of this work, and the original team who created the Artifact Genome Project, as without AGP, this project would not have been possible. Thank you, and we hope you enjoyed our presentation.